Hey class, welcome to Unit V, which is on the population variance. So in a sense, this is our first of the new number crunching units. But we're not quite there in terms of 307 because 307 is talking about how variables interact with each other. So we'll be taking a look at how does the gender of a person affect how they rate, say, the cleanliness of the bathrooms or something in a restaurant. So we'll be looking at bivariate, so bi meaning two, variate or multivariate analysis. At this point, this is kind of a transition unit. This is still univariate in that we're talking about just analyzing one column of numbers from a spreadsheet, from a data set. And so it's just focusing on one variable. Let's take a look at the symbols that we've been introduced to in our first stats course. And so we've got population values, of course. And then we've got the equivalent sample values. And just to remind you of the symbols that we have here then, we have, of course, the size. Actually, let's write these over here. So we've got the size, we've got the mean, we've got the standard deviation, and then we've got the proportion. And those symbols then are big N for the population, little n for the sample. For the mean, we use the Greek letter mu, and then x bar is the sample mean. For the standard deviation, we're talking about sigma. And of course, the variance would be sigma squared. So that's what we're talking about, is either sigma or sigma squared. That's fine. And then S would be the sample standard deviation. And then proportion, we had P and we have P bar. So in this particular unit here, what we're doing is we're focusing in on this one right here. In 306, what we did was we focused in on doing tests and confidence intervals for the mean and for the proportion. So now we're taking a look at the variance, or its square root, of course, the standard deviation. And so in stats, actually, you can measure any population parameter, but this is the one that we're going to focus on in this particular unit. So this is taking a look at the variance or the standard deviation, right? One's just the square root of the other. So let's take a look at the topics that we'll be looking at here are, we'll take a look at something called the Chisquared distribution. So you will be introduced to a new distribution in this particular unit. And then we'll talk about how to do hypothesis tests using both a classical and a p-value approach, and then confidence intervals for the population variance. So just like we did in really the last main unit in Business 306, where we looked at hypothesis testing, and then the unit before where we looked at confidence intervals. So let me back up here actually just to a blank page here for a moment here. And let's talk about that whole concept of a sampling distribution. And so let's take a look at an original population. And whether it's normal or not really isn't the important thing, because if you have sample sizes large enough, then of course you've got the central limit theorem kicking in. And so we've got some mean, and then we've got some standard deviation of the x's. And then what we can do is we can start taking samples. So we're going to take, I'll just show these as kind of red dots here. And what we do then is we take all of these values here and we come up with a single x bar value. And then we could do that again like this, and we could come up with another x bar value. And of course that could get very messy very quickly, because we could take all combinations of a certain size n, let's say n is 30 or something, then we could come up with a distribution of all the possible sample means. And it would actually be a lot tighter than the original population. But according to the central limit theorem, if the original population's normal, then I guess it's the first limit theorem, but more generally, regardless of what the distribution looks like for the population, if your sample size is at least 30, then you would end up with a distribution of x bars, so sample means, which are normally distributed, and they're centered on mu, the population mean, and we have sigma over the root of n is the standard deviation. Of course, that's the central limit theorem. The thing is that when you take a sample, of course, you can calculate a mean, but you can also calculate a standard deviation. And so with the standard deviation, what we do is we could say, instead of coming up with an x bar value, then we could actually come up with an s squared value, either an s or an s squared value. We tend to look at variances here in this particular unit here, and of course the square root is the standard deviation. So let's take a look at the variance of a particular sample. And then of course this particular one has a variance as well. And so just like we did above, where you could take all possible samples of a certain size n and then calculate a mean for each, we could do the same thing and calculate a variance of each. And what we would end up with is a distribution, not of the x bars, but of the s squares. And so it would look like this. Let me actually get rid of this guy here. And we would end up with a distribution here of all the possible s squares that would look like this. Like that. Now, what's interesting about this is that it has a starting point of 0, because of course when you're talking variances, you can't have a negative variance, right? It's a squared number. And then it can go very high. You can have highly skewed values up here. So it tends to start at 0 and then it's skewed to the right like this. And so that's what the distribution of all possible s squared values are. Now, let's go back to, and I'm just going to tuck this into the corner here. Remember, we had our distribution of all possible x bar values, and it was normally distributed. And what we could do from there is we could convert that into a distribution of z values. Oops, that should be in the middle, but anyways. And so it has a mean of 0 and a standard deviation of 1, and these are the distribution of z values. So that distribution of x bars becomes a distribution of z's. That's, of course, the process of standardization. We can do the same thing here, where this thing here is standardized. Let me change colors here to something which actually has the same shape, just like the z distribution had the same shape here as this guy. This is a distribution called the chi-square distribution, and it is centered on 0, and actually the mean is equal to its degrees of freedom, which at this particular case is equal to n minus 1 for this unit, but it is going to be different when we get into the next couple of units here. So that will change when we get into bivariate analysis. But that's what the distribution looks like. So just like we did up here with the x bars, converting them into z's, we can convert any s squared into a chi-squared value, like that. Now, let's actually head back over here then and take a look at this thing. And the chi-squared distribution is, I said it looks like this. And it's very dependent on its degrees of freedom. So if this is the original distribution of the x's, and I guess in math terms we would say this is f of x, although you don't have to remember that, then the distribution is highly skewed. So it actually looks like this. And this would be for 1 degree of freedom. 1 degree of freedom. This would be a distribution for, say, 4 degrees of freedom. So you can see that skewness there. skewed to the right. By the time you get up to about an n of 30, you actually end up with something that is pretty normal looking. So this would be 29 degrees of freedom. And you can see that it's like a binomial distribution, that as your parameters increase, in this particular case our n for unit v, as our n increases, then this thing starts to look more and more like a normal distribution. That was the same thing that we found with the t distribution, right? It was very flat, but as its degrees of freedom increase, then it looks more and more normal. So that's what we've got there, and usually we'll be dealing with sample sizes that make the thing look fairly normal, but I'll always draw it so that it's skewed, and just to distinguish it from a z or a t distribution. So chi-square distribution I'll always draw this way, like this, and even though it might look actually fairly normal. So that's it. The other thing I just want to introduce you to, and it's not something that I tend to focus much on, but the Greek letter nu is, it's actually kind of a funny looking V here. It's your degrees of freedom. And so in our particular case then, in this unit, is equal to n minus 1. So sometimes you'll see that it's actually where we get our n from. It's Greek letters, so alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu. And so mu is the 12th letter, which is where we get our m from, and then nu is the 13th letter, and that's where we get our n. So m and n, mu and nu. Okay, that's just kind of an aside. You don't have to really remember that. But if you do see this symbol here then, that looks like kind of a funny looking V, that's actually a nu, and it means your degrees of freedom. This is really important here, and that is the expected value. And the expected value is the mean of the distribution, is the degrees of freedom. So in the center of the distribution you have not 0. Remember, you actually start at 0 on the left-hand side. It's not 0 like in a t and a z distribution. It's your degrees of freedom. So in this unit would be n minus 1. All right, let's take a look at how we read the table now. And so this is a new distribution, so there's a new table that goes with it. So let's see, I'm on page 51 right now. I'm going to jump to page 221, which is right at the end of your manual here. And here's the chi-square distribution. So I'm just going to back up and say this is the part where we have our tables here, right? And so we've got the normal table, and then we've got the t-table. Let's just stop here at the t-table, and with the t-table, down the left-hand side, you've got your degrees of freedom. And then across the top here, then you've got various values of alpha or alpha over 2, depending on what kind of problem that you're dealing with here. So they're talking about the area in the upper tail. The thing about the chi-square distribution is that it's not symmetric about 0, right? So you can't say that the lower tail value is just simply the negative of the upper tail value. All right, so it's not symmetric, it's skewed to the right, and it doesn't have 0 in the middle. It actually has its degrees of freedom. Because of that, we actually have to have twice as many columns. Now, what I've done is I've put a red line in here, and my suggestion is that you do the same, because what that does is it divides the left-hand side stuff from the right-hand side stuff. And so if you take a look at the very top here, you'll see that these numbers in this line here then show the percentage in the left-hand tail, 0.5%, 1%, 2.5%, 5%, and 10%. And then these values here show the area in the right tail. And so that's what we've got here. So if you take a look at any particular line, our degrees of freedom, let's say 6, you would see that that's in between these two values here, 1.61, which is on the left-hand side of it, and then 9.24, which is on the right. And of course, the numbers get smaller as you go to the left and bigger as you go to the right. And 6 is not halfway between those two numbers because the distribution is not symmetric. Okay? So given that, let's go and calculate some probabilities here. And so I'm going to go back here to, let's see, page 51. And we will get to this particular formula right here a little bit later here. But let's take a look at how we do this here. So what is the chi-square table value for 4 degrees of freedom, yielding 5% of the distribution to the right? Let's draw a little picture of that. So what we're talking about, so I'm going to draw always a chi-square distribution as being skewed like that. And what I always do is stick in here your degrees of freedom in the middle. So it's going to be 4. This is going to be a chi-square distribution with 4 degrees of freedom, just like we had a t distribution with its degrees of freedom. And then we go and we take a look at 5% in the right-hand tail. So that would be like this. That would be 5% here. So of course that could be an alpha when we get into hypothesis testing, right? So what is that particular value? Let's take a look at the chi-square table. And it's pretty easy. All we do is we go and we say, okay, 4 degrees of freedom. And we're talking about the upper tail here. So we're looking at 5% to the right, 95% to the left. That gives us 9.49. So that's your answer right there. And let's go back there. And so that particular number would be, here, I'm just going to put a little dot here and say that that's 9.49. And you can see that it is higher than 4. Of course, at the very bottom, we've got 0. And so it's always good to take a look and see, did that make sense when you checked it out here? All right. I'm going to leave this one here for homework. So I want you to figure out what is 5% of the distribution to the left. And now let's take a look at the next ones here. I'm going to actually leave this one here for homework because the next one will help explain this. So when it says, let's just take a quick look at number 3. When I've got the notation here, what is chi-square 0.01, comma 20? It's always, the first number is always talking about the area to the right. So this would be 1% in the upper tail with 20 degrees of freedom. So I'd like you to go and find that. Let's do the same with this one, where this is taking a look at, this is number 4, and so we're taking a look at chi-square 0.90. So if we look at a chi-square distribution here, like that, we're talking about 72 degrees of freedom. So 72 would be in the middle. And the number that we're given here is 0.90. So that's talking about 90% going up and 10% going down, right? So that first number there would always be the area going up. And so the equivalent would be 10% going down. So let's go to 72 degrees of freedom, the 10% column on the left-hand side. And we're going to get, let's see, so 72 degrees of freedom. I guess the closest that we have here is 70 degrees of freedom. So we'll have to go with that. And then we're going to the 10% column to the right. To the left, 90% to the right. So that turns out to be, it looks like 55.3 is the answer there. 55.3. By the way, while we're here, and I'll go and write that answer in a second, but while we're here, I'd like you to take a look then at these guys right here. Now, can I change those? I'm not sure if I can rotate those. Yeah, I'm not sure if I can rotate those, folks. Sorry about that. So there must be a way to do that. So you're going to have to kind of turn your head on this one here. But what I want you to note here is a couple of things here. We're really dealing with p-values here. P-values is where you're looking at what is the area. Sorry, we're talking about critical values, that's better, where you're given an area, like an alpha, and then you're trying to find out what is the equivalent chi-square value. So in this particular case then, we've got the z, we've got the t, and here's the chi-square distribution right here. And if you take a look at the lower tail, then we're using something which is just simply a chi-square dot inverse. And then you put in alpha, and then degrees of freedom. If you're talking about the upper tail, then you use a chi-square dot inverse dot RT for right tail. And then you put in your alpha for your upper tail and your degrees of freedom. And the reason why you need two different functions is that it's not a symmetric distribution, so you can't simply find one and say that the lower tail value is the negative of the upper tail. All right? So that's something to keep in mind. When we get into the next couple of problems here, the ones at the bottom of the page, they'll be dist functions. So it'll be the same kind of thing here where we'll use a chi-square dist, and we'll put in your chi-square value, your degrees of freedom. That will be for the lower tail, and then the upper tail will be exactly the same, except that we'll put in an RT here. So sorry that is sideways, but if you go and take a look at that, it will make sense. Let's go back here. So we found that this particular number here was 53, and that is, and of course we've got a 0 right here. So that was the answer that we had for number 4. Okay. Number 5, I'm going to leave you for homework, but I want to show you where we're going on this one here. So remember I said that as your degrees of freedom increase, that the chi-square distribution looks more and more like a normal distribution. You can actually use the normal distribution to find chi-square values for high degrees of freedom. The chi-square table, I think, goes up to about 100. Let's just go back there and see. Yeah, it goes up to 100 down here. So if you have more than 100 degrees of freedom, what you need to do is to use this formula, which is this guy right here. Now, this is in your formula book. So several pages back here at the beginning of your formula book, you'll see that. But what it says here is the chi-square value is equal to 1/2 times the equivalent z value plus 2 times, and then this, remember, is nu, which is your degrees of freedom, minus 1, and then squared. It's a goofy looking thing, but you actually get really, really similar results there. So in other words, let's take a look here. When we're talking about, this is number 5, chi-square 0.95, 200 degrees of freedom. Of course, the 200 is large. It's greater than 100, so we can't go straight to a chi-square table. But what we notice is that this is 0.95. So that would be the equivalent to 95% up and 5% down. Now the question is, if this were a z distribution, what would this value be on a z distribution, centered on 0, standard deviation of 1, what would that value be that has 5% in the lower tail? As soon as you figure that out, you can plug that into this formula at the top here, and you will get the chi-squared value. I'll give you a hint. It's somewhere in the area of about 165-ish. Not quite that. It's a little more than that, but that'll give you an idea. If you get something in the 160s, you'll be in the right place there. All right, let's do one more here. I'm going to do number 7 and then number 6, and then I'll leave number 7 for homework here. So let's take a look at number 6. Where does 4 fall on a chi-square distribution with 13 degrees of freedom? This really is a p-value kind of problem here. So here's a chi-square distribution, 13 degrees of freedom, and we're looking at 4 right here. So we want to figure out what is this area here. It's really just the p-value. Okay, so let's go and take a look at this. We'll go back to page 220. Oops, I said 222. There we go. 221. And so we're going to go to 13 degrees of freedom right here. And we're going to look across here until we find 4. And you can see that 4 falls right here, which is between 0.5% and 1% to the left. Now, it's also equal to 99% and 99.5% to the right, but we'll just look at it in terms of 0.5% and 1% to the left. So it's just like reading a t-table in this way. 4.0 falls right between 3.57 and 4.11. I will go back there and see, that was 3.57 and 4.11. So what we've got here is, and this is going to be not to scale, of course. Here's the 3.57, and that corresponds to 1%. And then you've got oh, sorry, that would be 3.57 here. This would be 4.11. I don't know where I got the idea that 3.57 was halfway between, or partway between 4 and 13. Okay, so there's the 0.01, and this would be 0.005. So what we have here then is that this area here, which is really the p-value, is the probability of getting a chi-square value of 13 degrees of freedom being less than 4, which, when we get into hypothesis testing, is really just the p-value, is something less than 1% and something greater than 0.5%. So that's how we do that. So I'm going to leave you with number 7 here, and that will take us then into hypothesis testing after that. So let's end the video at this point. Thanks for tuning in.